This lecture deals with minimum spanning tree algorithm. So, before defining minimum spanning tree, what do you mean by a spanning tree? Spanning tree of a connected graph, undirected graph, is actually a tree that spans over all the vertices. So, if we consider this undirected graph, so I can say that this is a spanning tree. So, let this vertex be A, C, B, D, E. Again, I can have another spanning tree A, B, D, C, E. So similarly, you can identify a few more spanning trees. So this is called a spanning tree of this connected graph because it is a tree, that is a graph without a cycle, and it actually spans over all the vertices. This tree contains all the vertices, and this graph will, or the vertices will stay together as a single connected component. So that is what you mean by a spanning tree. So minimum spanning tree is actually defined for weighted graph. So if you consider this weighted graph, you can have multiple spanning trees. So if you add weights, this edge is having weight 4, 2, 2, 8. So as far as this spanning tree is concerned, the total cost is 10, 14, 16. Cost is 16. Now if I consider this spanning tree, this weight is 7. This spanning tree is of cost 19. So I can identify another spanning tree C, B, D, E. So here cost is 2, here it is 2, 2, 8. So total cost is 8, 10, 12, 16. Oh, rather than adding this particular edge, you can add this edge. So cost is 8. Now I can identify another spanning tree structure like this: A, C, B, E, D. So here cost is 8. So if you consider total cost is 27. So given a weighted undirected graph, you can have multiple spanning trees, out of which some spanning trees will be having minimum total edge weight. So that spanning tree is termed as the minimum spanning tree or minimal spanning tree. So in this case, this is one minimum spanning tree. So here total cost is 16, which indicates that you cannot identify another spanning tree whose total edge weight is lesser than 16. So you can have another spanning tree whose total edge weight is 16, which implies that you can have multiple minimum spanning trees for a given graph. So if I consider this particular structure, spanning tree, cost is 16. For this spanning tree also cost is 16. So these are the two possible minimum spanning trees for this. You can identify multiple minimum spanning trees for a given graph, and it depends upon the edge weight also. But you cannot identify a spanning tree whose cost is lesser than the minimum spanning tree. So that is a fact. Now there are two classical algorithms that computes or determines minimum spanning tree. One is Kruskal algorithm and the other is Prim's algorithm. So this lecture deals with Kruskals algorithm. So let me illustrate the working of Kruskal algorithm using this example. So the first step involved is sorting edges in ascending order of edge weight. So if I try to sort it in ascending order, so first edge it could be CB whose cost is 2, next one is BD whose cost is 2, next one is CD whose cost is 3, you can have AC whose cost is 4, next one is AB whose cost is 7, next one is BE cost 8, next one is DE with cost 8. So that is the first step. Now if we consider the actual algorithm, it will try to pick the edges one by one in this ascending order and add it to the tree, spanning tree. So as you all know, since this graph is a connected graph, the resultant spanning tree contains all vertices. So these are the vertices. Now this is the spanning tree that I am going to build. Now pick edges one by one. So first you are going to take this particular edge and we will be trying to add this edge into the current spanning tree. So you cannot treat this as a spanning tree. This is actually a forest at present with 5 different trees. So each node will act as a separate tree. Now take the first edge in this ordered sequence, add it to the current T. So if I add CB, so before adding CB, I have to verify whether C and B lies in 2 different sets or 2 different components. Or in other words, you have to check whether C is reachable from B or not. Since B is not reachable from C, or since C is not reachable from B, I can say that C and B lies in 2 different components and this edge is treated as a safe edge. So this is a safe edge, you can add it. Now take the next edge, BD. So before adding BD, I have to check whether B and D lies in 2 different components. So here B lies in this component and D lies in this component. So since B and D lies in 2 different components, edge BD is a safe edge. So an edge is said to be a safe edge if addition of that edge into the current forest or tree will never generate a cycle. Now consider next edge CD. So if I try to add this edge CD, that will create a cycle which violates the property of spanning tree, or it fails to satisfy the condition of spanning tree. So this edge is not a safe edge. So you have to reject this particular edge. This edge get rejected. Now next edge is AC. So you will be checking whether A and C lies in 2 different components. So A is in this component and C is in this particular component. So AC is a safe edge. Now you will be taking AB. If I check A and B lies in the same component, in the sense B is reachable from A. So this edge is not a safe edge. Next edge selected is B. So you will be checking whether B and E lies in 2 different components. So B actually lies in this component and E lies in this component. So B is a safe edge. Now you will be taking the next edge D. So if I take D and E lies in the same component, which indicates that the edge is not a safe edge. So this edge gets rejected. So these are the edges that become part of the spanning tree. And if we calculate the total edge weight is 16, which is the total cost of minimum spanning tree. So this is the basic idea behind the working of Kruskal algorithm. And from the implementation point, different endpoints of a given edge lies in two different components. We can use the disjoint set structure. Disjoint set data structure. So let me explain Kruskal algorithm from the implementation aspect using disjoint set data structure. So first step is sorting edges in the ascending order by weight. Now for each vertex you have to perform make set. So you will be calling make set A, you will be calling make set B, similarly make set C, make set D and make set E. So if you are having 5 vertices, you have to execute make set 5 times, so you will be getting 5 singleton sets. Now you have to initialize an empty set. So this set is actually used to maintain the set of edges that become part of our spanning tree, or the set of safe edges. So first you are taking CB. So you will be checking whether find set C not equal to find set B. So what about find set C? If I execute find set C will return the representative of C set containing C. So representative is C itself. So find set C will return C, and if I execute find set B will return B itself. So representative member is the first element in that set. So since find set C and find set B are different, you can say that B and C lies in two different sets, or B and C lies in two different components. So if this condition is satisfied, edge CB is treated as a safe edge and CB will be added to spanning tree. And you can perform union of B and C. So you will be getting a set containing BC. So next you will be taking edge BD. So you will be executing find set B, checking find set B not equal to find set D. So what is find set B? So this is the set containing B. Find set B will return the first element of this set. So find set B is B itself. What about find set D? Find set D is D itself, because D is the first element in the set containing D. So since these two are different, this condition gets satisfied, which indicates that BD is a safe edge. So you can add BD. So while adding BD, you have to take union of these two sets, or take union of sets containing B and D. So you will be having B, C, D. Now you will take CD. You will be checking find set C not equal to find set. C is the first vertex and D is the second vertex. Find set D. So what about find set C? Find set C is the first element in which C belongs to, that is B. Find set C will return B. What about find set D? Find set D will return the first element in which D belongs to. So it will return B itself. So this condition fails because C and D, since C and D lies in the same set, it will return B. So this edge is an unsafe edge. You are not allowed to add this edge. Next one is AC. So you will be checking find set A, that is A, and find set C, that is B. Since A and B lies in two different, A and C lies in two different components, AC is a safe edge. Since AC is a safe edge, you have to unite set containing A and C. So this will be the end result, ABCD. Now you will be taking AB. So what about find set A? Find set A is A itself. find set B, that is again A. So this indicates that A and B lies in the same set. So AB is not a safe edge. Next edge is B. So you will be executing find set B, that is A, find set E, that is E. So B is a safe edge, so B is added, and you will take union. Next one is D. Find set D is A and find set E is A, so this is an unsafe edge. So at the end this algorithm will return T, or T contains the set of safe edges or the edges that belongs to the minimum spanning tree. Now let me formalize this algorithm. So it will receive the weighted graph G as parameter. So what is the first step? Sort edges in G by ascending order of weight. That is the first step. Now, as I said, the second step is you have to perform make set. That is called make set for each vertex. Create n singleton sets where n is the number of vertices. So we can write for each vertex u belonging to vertices in graph G, do the following. So you have to call make set u. So this make set u actually creates a singleton set containing u. Now you can initialize the set of edges that become part of spanning tree to empty. So create a set empty set T. Then for each edge UV selected from the sorted list in ascending order, do the following. So you have to pick edges in the sorted list one by one in the ascending order, and you have to check if find set u not equal to find set b. So if find set u is not equal to find set b, then that means u and b lies in two different sets. So u is a safe edge. So if this condition is satisfied, then you can add edge uv to the spanning tree, followed by calling union uv. So union uv actually unites sets containing u and v. And at the end, if you want, you can return t, or at the whenever this algorithm terminates, t will contain the set of safe edges, so or the edges that become part of the minimum spanning tree. Now let me analyze this particular algorithm. Assume that your graph G is having V vertices and E edges. So first you have to sort edges in G by ascending order of weight. So you have to use a sorting algorithm that runs in E log E time. So you can use heap sort or merge sort, that will run in order of E log E time, since you have to sort E edges, E number of edges. Now what about total cost of make set operation? As you all know, a single make set takes constant time, and since we are having V vertices, you have to call V number of make set operation. So this total cost of make set will be order of V. Now if I consider cost of this particular step, you have to create an empty set or empty list whose cost is order of 1. It takes constant time. Now we are performing aggregate analysis. What about total cost of find set operation? See, you know that you are having E edges in the graph, and for each edge UV you have to call 2 find set operations. So for each edge UV you have to call find set U and find set V. So what about total number of find set operations? You have to execute 2E find set operations. So total cost for find set will be bounded by order of E. Now what about total cost for union operation? So if we go through the analysis of disjoint set data structure, analysis of union operation disjoint set data structure using weighted union heuristics, you know that if you are having V number of items or V singleton sets, in order to unite the V sets into a single set containing V items or cardinality V, cost taken will be order of V log V if we follow weighted union heuristic. So you can refer the Corman textbook and go through the analysis of union operation and disjoint set data structure using weighted union heuristics. You will find that total cost for union will be order of V log V for V singleton sets of V items. This is the cost for this union operation, disjoint set data structure union operation, order of V log V. Now this actually represent addition of the safe edge into the list of edges in the spanning tree. So that depends upon the underlying data. So you can use a structure array or you can use a linked list concept. So whatever the structure or data structure that you are using, addition of an edge into the current list will take constant time. And in this case, if we consider addition of edges, how many additions will be performed? Exactly performed. If you are having V vertices, in order to build the spanning tree, we need exactly V minus 1 edges. So this step will be executed exactly V minus 1 times and cost will be order of V. Now you can take the summation. So E log E. So which one is having highest growth rate? So from this it is clear that number of vertices will be always lesser than number of edges. So runtime will be runtime of this algorithm. So anyway, E log E will be greater than V, E, V and V log V. So you can represent runtime as order of E log E. So this is equal to order of E log V. So runtime is order of E log V. So the reason is that if I take E, so what about maximum number of edges? What about the upper bound of number of edges that can be inserted into an undirected graph? That is actually n into n minus 1 by 2 if graph is having n vertices. Here your graph is having V number of vertices. So total number of edges, maximum number of edges will be v into v minus 1 by 2, which is bounded by order of v square. So if I take an undirected graph with v vertices, maximum number of edges is bounded by order of v square. Now what is log e? Log e. So log e is equal to order of log v square, which is equal to order of 2 log v, which is equal to order of log v. So log e is equal to log v. For that reason, you can represent runtime as order of e log v rather than e log e. That's it.